We are in section 5.2, binomial probability distributions. Experiments in which only two outcomes are possible are referred to as a binomial experiment, provided certain criteria is met. So an experiment is said to be a binomial experiment if the following four requirements are met. So definitely something we need to know. First one says the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. Number two is going to be that the trials are independent. Most of the time they are, since we're dealing with people. This means that outcomes of one trial will not affect the outcome of another trial. 3 says for each trial there are two disjoint or mutually exclusive outcomes. We call them success and failure. And then number 4, the probability of success is the same for each trial of the experiment. Let the random variable x be the number of successes in n trials of a binomial experiment, and x is called a binomial random variable. So some notation here that we will be using. First one is there's n independent trials of the experiment. P is the probability of success. So 1 minus p, or we also sometimes will call that q, is the probability of failure for each trial. And then 3, let x denote the number of successes in n independent trials of the experiment, so that x is somewhere between 0, could equal 0, and n, and it could equal n. The example says, determine which of the following probability experiments represent a binomial experiment. If the probability experiment is not binomial, state why. So A says an experimental drug is administered by 100 randomly selected individuals with the number of individuals responding favorably recorded. So first thing is there is 100 random trials. So we have 100 trials. So it's a fixed number. The second thing is that these trials need to be independent, and since we're dealing with people, they're independent. Third thing is that there's two different outcomes, success and failure. So for this one, it's going to be if they responded favorably or not favorably. So favorably or not favorably. And then the fourth thing says that the probability of success is the same for each trial of the experiment. And it doesn't state that, so we will assume that. And so with that assumption, we can say that this is a binomial experiment. Part B says a random sample of 15 college seniors is obtained and individuals selected are asked to state their ages. So they're asked to state their ages, and ages are going to vary from probably like 17 or 18 all the way up. And so for this, there is more than two outcomes. And so because of that, this is not binomial. Part C says 500 randomly selected U.S. parents with at least one child under the age of 18 are surveyed and asked if they have ever spanked their child. The number of parents who spanked their child is recorded. So again, we have 500 trials. They are people, so we'll put down 500 independent trials. So that satisfies those first two requirements. Third one is that there's going to be two disjoint or mutually exclusive outcomes. And for this problem, it's either they spank their child or do not spank. And then again, we will assume that that probability would be the same for every single person. And so therefore, this is an example of a binomial experiment. The next example says when an adult is randomly selected with replacements, there is a 0.85 probability that the person knows what Twitter is based on results from a Pew Research Center survey. Suppose that we want to find the probability that exactly 3 of the 5 randomly selected adults know what Twitter is. So part A says, does this procedure result in a binomial distribution? So when you go through homework problems, and then also when you go through problems that are on a test, not everything's going to be a binomial experiment. So you're going to have to go through these requirements before you start the problem to make sure that you're actually dealing with a binomial distribution. So first one is we're going to have a fixed number of trials, and it does say there's 5 different people that they're surveying, so 5 trials. 2, they have to be independent, and they are since we're dealing with people. 3 is 2 disjoint or mutually exclusive outcomes, and they are you either know what Twitter is or you don't know. And number 4 is that the probability of knowing about Twitter is going to be the same for everybody, and that is fixed. And that probability this time we are given, it's 0.85, and it is fixed, meaning that it's not going to be different based upon your age, or it's not going to be different based upon your gender or your ethnicity or anything else like that. So part B, right below this, says if the procedure does result in a binomial distribution, which in this case it does, it satisfied all 4 of those requirements, identify the values of N, X, P, and Q. So N is the number of trials, which is 5. X is the number of successes. For us, it's 3. P is the probability of success, which is 0.85. And then Q is going to be 1 minus that 0.85, which is equal to 0.15. So right below this, it says when sampling without replacements and the sample size is no more than 5% of the size of the population, treat the selections as being independent, even though they're actually dependent. And then right below that, binomial probability distribution function. This is the probability of obtaining X successes in N independent trials of a binomial experiment is given by, and you'll see that combinations that we saw earlier in chapter 4. And so N choose X times P raised to the X times 1 minus P raised to the N minus X, where X is going to take on all the values from 0 through N, and P is the probability of success. Below this it says that when you're reading these problems, there's going to be certain phrases, and I put down those phrases here just to remind you guys of what symbol, what inequality that those would represent. So definitely add to this. If you see anything extra along the way, make sure to look these over, make sure you know these. So right below this is another example. This example says, according to flightstats.com, American airline flights from Dallas to Chicago are on time 80% of the time. Suppose 3 flights are randomly selected and the number of on-time flights are recorded. Part A says, explain why this is a binomial experiment and compute the probability for each value of the random variable. So first, let's talk about why this is binomial. I'm going to go ahead and just say it, so feel free to write down anything that you find helpful. So first one is going to be that there has to be a fixed number of trials. 3 flights are randomly selected, so we know that. The flights are independent of one another, and they're either on time or not on time, so we have 2 disjoint or mutually exclusive outcomes. And then the probability of them being on time is fixed. It's 80% of the time. So this is binomial. And then our number of flights that we have is 3. And the value that we have for our random variable x is going to take on anything from 0 up through n. So it could be 0 flights on time, 1 flight on time, 2 flights on time, or all 3 of those flights will be on time. And then the last thing that we need is our probability, which is that the probability that a flight will be on time, which is equal to 0.80. So we've explained why it's a binomial experiment, and now we're going to be computing the probabilities for each of these random variables, which are from 0 through 3. So the first thing we're going to do is write down the binomial probability distribution, which is stated up above, which is P of x equals, and it's N choose x, P to the x, 1 minus P to the N minus x. And so we have to do this for all the values of x, which is going to be 0, 1, 2, and 3. And so N in this problem we said is 3, and then x is taking on those different values. P is also fixed at 0.8, and then 1 minus P, which again you can write as Q. And so we're going to go ahead and substitute these all in, and then we'll use our calculator to calculate these. So let's go ahead and do the first one together, and then we'll fill in the rest of them. So the first one is going to be n is 3, x in this problem is 0, p is 0.8 raised to the 0 power, 1 minus 0.8 raised to the 3 minus 0, or just to the third. On your calculator, you need to go to Math, PRB or PROB, and go down to Combinations. The first number that we have is a 3, and then the second digit that we have is a 0. I'm going to use my right arrow so I'm not down in that little sub part, but again, every calculator works a little different. P is 0.8, and we are going to raise this. To raise something up to a power, you can use your caret. It's right above the division symbol, and it's raised to the 0 power. Again, I'm going to use that right arrow to get out of the exponent, and then I'm going to type in with parentheses 1 minus 0.8, close my parentheses, raise, so do the caret again, and this time it's 3 minus 0. I'm going to just type 3, select enter, and we get our probability. From your calculator, you get an answer of 0.008. So the next three, I'm going to go ahead and fill those in and write down the probabilities, but definitely try them on your own and then ask if you have any questions. So we are able to calculate the probabilities for each value of the random variable. Part B says to construct a probability distribution, and I'm going to go ahead and create a table of values. So it's going to be the value of x, which is our random variable, and the corresponding probabilities. So x is either going to be 0, 1, 2, 3, and then those corresponding probabilities we calculated up above in part A. So I'm just going to go ahead and copy those down. And this is my binomial probability distribution. So right below this, we have obtaining a binomial probability using a TI-83 or 84 calculator. So now we're actually going to be doing this, but instead of by hand, like what we just did with that formula, we're going to actually use the calculator to help us out. So for the first one, this is going to be when you're computing probability that x is equal to a certain value. So like we did when x is equal to 0, when x is equal to 1, 2, and 3 in that last example. And so to do that, we could have used binom PDF. And to get to that, we go second vars, binom PDF. And then you need to enter in n, p, and x. Again, n is the trial, p is that probability of success, and x is that random variable that it's taking on. It also has the next one is the probability that x is less than or equal to x. So to access this on your calculator, you go second vars, and it's binom CDF. The binom PDF that we had first was our probability distribution function. CDF stands for cumulative distribution function, meaning that that value in everything smaller than it, which we had by definition before. And so to do that, same idea, we enter in n, p, and x. Now if you notice, we have equals to and less than or equal to. We do not have anything where we have the probability that x is greater than a value. And so in order to do this, we actually use the idea of complements. So this is going to be 1 minus the probability that x is less than or equal to a value of x. This is another one that we need to know. So right below this, there's an example, and it says, according to flightstats.com, American airline flights from Dallas to Chicago are on time 80% of the time. Suppose 15 flights are randomly selected and the number of on-time flights are recorded. So this is the same problem that we saw before, but instead of 3 flights, we're now dealing with 15 flights, so a larger sample here. And we know that this is binomial, since we already discussed that in that last example. So part A says, find and interpret the probability of exactly 10 flights being on time. So it does say probability that x is exactly, which means equal to 10. So from using our calculator, we can either do binom PDF or binom CDF, and I want you to note that because it says exactly 10, that is equals to, and so we're going to be using what's called binom PDF. And I'm going to go ahead and write down those steps. which I suggest doing because when you go back and you study, sometimes you don't remember what you did to get that result on the calculator. And so for binom PDF, we have to put down N. N for this one is equal to 15. We have 15 flights this time. Our probability of it being on time is still 0.80. And then for this problem, our x value is 10. On the calculator, you're going to go to second, vars, go down to binom PDF, and we need to put in the number of trials, our probability, and then x. So our number of trials was 15, probability is 0.8, and the x value here is 10. Close your parenthesis, press enter, and we get our from the calculator, we get a probability of 0.1032. It also does say to interpret. And so to interpret this, we would say that the probability that exactly 10 flights out of the 15 flights are on time is equal to 0.1032. So part B says find and interpret the probability that fewer than 10 flights are on time. So probability that, and fewer means less than 10 flights are on time. Now looking at the calculator steps up above, it does look like binom CDF. However, this binom CDF, remember, cumulative distribution function, is that value and everything below it. So it needs to have a less than or equal to symbol, which this one doesn't have. So I'm going to rewrite this. And because we're dealing with discrete probability distribution functions, I know it's binomial, but discrete data, we are counting by whole numbers. And so if less than 10 flights are on time, I know that that means less than or equal to 9 flights are on time. It means exactly the same thing. So from this, we can use binom CDF. Again, your value for n is 15. Probability of it being on time is 0.80. And then our x value is equal to 9. On your calculator, go to second, vars, go down to binom CDF. Our number of trials is 15, probability is 0.8, and this time our value of x is equal to 9. Select enter, and we get our probability. From the calculator, you get a probability of 0.0611. And then again, it does say to interpret. So interpreting this, we can say the probability that fewer than 10 flights are on time out of the 15 flights is equal to 0.0611. So the next example that we have says, find and interpret the probability that at least 10 flights are on time. So still a probability, but this time it says at least 10 flights are on time. So at least means x would be greater than or equal to 10, which again, we know that we don't have that option with our calculator, but we have to use what's called the complement, which we saw back in chapter 4. So we're going to have to do 1 minus, and since I'm talking about 10 and larger means I want 10 flights on time, 11, 12, 13, 14, or 15. The part that I could take, which would be 100 or 1, and subtract away what I do not want, which would be the probability that our flights are less than or equal to 9. And so we can go ahead and plug this in on our calculator, or you can use what we already calculated in part B. I'm going to assume that we don't have that, and you would just type in 1 minus and then do binom CDF, and then 15, 0.80, 9. So we're going to do 1 minus, since we're using the complement, and then I'm going to go second, vars, go down to binom CDF. 15 is our n value, p is 0.8, and this time our x is 9. Select enter, and we get our probability. So from your calculator, you get 0.9389. Part D says find and interpret the probability that between 8 and 10 flights are on time. So between 8 and 10 means that it could be either equal to 8, 9, or 10. So you can do this and calculate each of those probabilities independently and say probability of x equals 8 plus the probability that x equals 9 plus the probability that x equals 10 and use binom PDF to get that. Or you can go ahead and use binom CDF. And I'm going to go ahead and do it that way, but definitely ask if you have any questions. And so I'm going to take probability that x is less than or equal to 10, which would be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. But I don't need all those values. I want it to stop at 8. So I need to subtract away probably that x is less than or equal to 7. On our calculator, we're going to go to second vars, go down to binom CDF, 15, 0.8, 10, minus, and then we're going to go ahead and do binom CDF again. So second vars, binom CDF, still 15 trials, 0.8 is our probability of success, and this time our x value is 7, close parentheses, select enter, and we're going to get our probability. Again, you can do this by using binom PDF for 8, for 9, and for 10 independently, and then adding those together. So on the calculator, we get an answer of 0.1600. And again, this one does say to interpret. And since we're interpreting this, we would say the probability that between 8 and 10 flights are on time out of the 15 flights is 0.1600. Right below this, we have a few little formulas that we need to know. So the mean, the expected value, variance, and standard deviation of a binomial distribution. A binomial experiment with n independent trials and a probability of success p has a mean equal to mu, which is n times p, variance, which is sigma squared, which is n times p times q, or 1 minus p, and then a standard deviation, which is equal to the square root of your variance. It is very important to interpret and understand the mean and the standard deviation, so the range rule of thumb and the rare event rule for inferential statistics can be helpful. So that range rule of thumb, again, for those significantly low values, significantly high values, and values that are not significant are given. And so again, significantly low are less than or equal to mu minus 2 sigma, significantly high are greater than or equal to mu plus 2 sigma, and then again, not significant would be between those two values. So the example right below this says between 1974 and 2011, there were 460 NFL football games decided on an overtime, and 252 of them were won by the team that won the overtime coin toss. Assuming that winning the overtime coin toss does not provide an advantage, then P is equal to 0.5 and Q would also be equal to 0.5. Part A says find the mean and the standard deviation for the number of wins in a group of 460. So the mean is equal to N times P. N is the number of games, which is 460, and P, which was stated up above, is 0.5. So this works out to being 230 games. And then our standard deviation is equal to the square root of n times p times 1 minus p, or you can write that as a q, which is going to be the square root of 460 times 0.5 times 1 minus 0.5. And working this out, I'm around 2 decimal places, you get 10.72 games. Part B says use the range rule of thumb to find the values separating the numbers of wins that are significantly low and those that are significantly high. And so those formulas that were written up above for significantly low cutoff is going to be mu minus 2 sigma, and significantly high would be mu plus 2 sigma. And we have our mean and our standard deviation from part A. So I'm going to go ahead and substitute those in. So we have 230 minus 2 times 10.72, and then 230 plus 2 times 10.72. So working these both out, the first one that we have, rounding 2 decimal places, is 208.56, and the second one would be 251.44. And the units here would also be games. So these are the cutoffs. So pretty much anything that is 208.56 games or less is considered significantly low. And so I'll put significantly low over here. And then significantly high is going to be 251.44 games or higher. So part C is asking, is the result of 252 overtime wins in the 460 games significantly high? And so is it larger than 251.44? And yes, barely, but it is. So 252 is significantly high because it's greater than that cutoff of 251.44 games. So we can also think of the same idea with probabilities. So using probabilities to determine when results are significantly high or significantly low. And for both of these, it's going to be when we have the values that we get are going to be less than or equal to 0.05. That was our magic number cutoff. So significantly high number of successes is when we have a probability of X or more, but it's less than 0.05. And then significantly low number of successes is going to be the probability of X or less or fewer is less than or equal to that 0.05. So the next example that we have says data on M&M's weights contains information on 100 M&M candies and 19 of them are green. Mars company claims that 16% of the plain M&M candies are green. For the following, assume that the claim of 16% is true and assume that a sample consists of 100 M&Ms. Part A says use the range rule of thumb to identify the limits separating values that are significantly low and those that are significantly high. Based on the results, is the result of 19 green M&Ms significantly high? So first thing is, this is binomial. We have 100 M&Ms. They are independent of one another. Two different outcomes. It's either green or not green for this case. And we also know that that probability of them being green is fixed. It says that it's true to be 16%. So with that said, we know that N is equal to 100 and P is equal to 16% or 0.16. And so part A says use the range rule of thumb to identify the limit separating the values that are significantly low and those that are significantly high. Based on the results, is the result of 19 green M&Ms significantly high? So in order to do this again, we need to calculate our mean, which is N times P. So we have 100 times 0.16, which works out to be 16. And our standard deviation, which is the square root of N times P times 1 minus P, which is the square root of 100 times 0.16 times 1 minus 0.16. And when we work this out, we get 3.67. And so our cutoff for significantly low would be mu minus 2 sigma, and significantly high would be 2 plus 2 sigma. So go ahead and plug those values in. So we have significantly low and significantly high. So for the significantly low cutoff, we get 8.66, and this is green M&Ms. And significantly high is going to be 23.34 green M&Ms. So it also asks, based on the results, is the result of 19 green M&Ms significantly high? And so significantly high would mean that 23.34 or larger are considered significantly high. So 19 is not significantly high. It's also not significantly low. I know it doesn't ask that, but significantly low would be anything less than that 8.66. Part B says find the probability of exactly 19 green M&Ms. So again, probability exactly 19 would be X is equal to 19. And again, since we know that this is a binomial distribution, we're going to go ahead and use binom. PDF since it's an equals to sign. N is equal to 100, P is equal to 0.16, and X is equal to 19. Calculator, you're going to go to second, vars, go down to binom PDF, and our value of N is 100, success is probability of 0.16, and then our X value here is equal to 19 green M&Ms. Select enter and we will get our probability. On your calculator, you get an answer of 0.0736. Part C says find the probability of 19 or more green M&Ms. So the probability of 19 or more green M&Ms would be greater than or equal to 19. And again, we do not have this option with our calculator, so we have to use complements and subtract away what we do not want. And so I'm going to do 1 minus, and then we do not want anything that is smaller than 19 or 18 and less. So the probability that X is less than or equal to 18. So we can type in 1 minus and then go to binom CDF, and we have 100 for N. P is 0.16, and this time our X value is 18. So for this problem, we have to use the idea of complements. So on our calculator, we're going to do 1 minus, and then we need to use binom CDF. So go to second, vars, binom CDF. Trials is 100, comma 0.16 for our probability of success, and then comma our X value, it'd be 18. Select enter, and we get our probability. So from the calculator, we get 0.2424. Part D says which probability is relevant in determining whether the results of 19 green M&Ms is significantly high. The probability from part B or from part C. And it says based on the relevant probability is the result of 19 green M&Ms significantly high. So it would be, for it to be relatively high, that means that we have to be looking at that value in greater than. So part C, because it is 19 or more. And we have, it says, based on this, is the result of 19 green M&Ms significantly high? And our probability of X greater than or equal to 19 is equal to 0.2424, which is not less than 0.05. So we can say that it is not significantly high. From part A, which was also asking about 19 green M&Ms being significantly high, we said no, it's not significantly high. And so it matches with this one because our probability is not less than that cutoff, which was 0.05, or super unlikely to occur. So part E says, what do the results suggest about 16% claim on Mars Company? It was fine if we had this 19 green M&Ms or 19% of them. So the result does not provide evidence against the claim of 16%. So it's not unusual. So result does not provide evidence against the claim of 16% for green M&Ms.